So, a very good morning to all the dignitaries, guests, teachers, parents, and our beloved students with great joy and immense exultation. I, Ghazal Soni, on behalf of Disha Delphi Public School, welcome you all. It's really an honor to be here and present in front of you the new things which we are going to learn today. So today we have gathered here to learn new things and new possibilities in the field of mathematics on the account of Yellow Pig Day. What could be better for a teacher than this, that his or her own student soar high in the sky, exploring and opening new gates of possibilities, not only for him, but for everyone else and for the whole humanity. So, with great pride in my heart, I would like to introduce you all with the key speaker for today's webinar, Master Anand Kumar, a math enthusiast who has become an epitome of insightfulness and excellency in just a short span of his life. So, before I ask him what is Yellow Pig Day, I would like to relate you with all the achievements he has accomplished till now in his life. He was known as the Jupiter among his classmates for the vastness of knowledge he has in his subject. The list of his achievements is a very long one, so let me start with that. He, being a grade 12 student of Disha Delphi Public School Kota, received Ramanujan Fellowship Award 2020 in USA. This award is given to the math wizards who display a great potential and excel in mathematics. So we can say among us today we have a math wizard, and it's really a privilege and honor. It will also please you and fill you with pride to know that our Master Anand is among the 5 recipients who have been awarded Pradhan Mantri Rashtriya Bal Puraskar for excellency in the field of scholastics. His achievements do not end here. His 2 research papers on sums of polynomial type exceptional units and on questions of X units were published in international journal Archive der Mathematik, Springer, Switzerland in December 2019. Interestingly, he co-authored the papers with 2 PhD scholars under the supervision of Harish Chandra Research Institute, Prayagraj. Apart from this, he has been a speaker and delivered talks on his research papers in different events across country. One such program was Mathematical Association of America, Math Feast, where he introduced polynomial notion of exceptional units. He also holds All India rank 12 in Indian Mathematics Olympiad 2021 and rank 1 in Indian National Mathematics Olympiad merit list. The list of his achievements can go on and on and on. His keen interest in maths sparked at a very early stage, and since then he never looked back and consistently making progress in his life in his favorite subject, maths. So now, without further ado, I would like to turn the time over to Master Anand to make us feel inspired and astonished again at the same time by his intellect and mental skills and capabilities, and also tell us about what is Yellow Pig Day and what significance it holds. So, Master Anand.
Good evening, everyone. Thank you, ma'am, for the brief introduction. So, uh, I would like to quickly introduce myself. I'm Anand from grade 12, and I'm here to present to you all about the Yellow Pig Day. So, let's start. So, first of all, the question that arises in the mind is what is the National Yellow Pig Day, and what has it to do with today, like July 17? So let's try to answer these questions first. So, what is Yellow Pig Day? It all started with a mathematical discussion between two students from Princeton universities in 1960s. They were kind of analyzing the number 17, like various properties about this number and why is it so special and so on and so forth. Eventually, I don't know why, but this turned out to be a joke. Like they invented the concept of a yellow pig with 17 toes, 17 teeth, and so on. So why was the pig yellow? Well, really no one knows. Like maybe it was just a creative imagination of them. Since then, Yellow Pig Day is an important part of the academic calendar and people usually celebrate it with cakes, carols, etc. For a fun fact, did you know there's a Yellow Pig Day carol? You can probably Google that out. It's pretty fun. Okay, so why is it celebrated on 17th July? Like, what's so special about the number 17? Let's analyze that. So I'll be stating a few fun facts about the number 17 and why is it special. So one thing is that 17 is a prime number. If you're wondering what is a prime number, then a natural number n is said to be prime if it has like exactly two distinct positive divisors. Say for example 17. If you look at the positive divisors of 17, it's 1 and 17, nothing else. So it has got two positive divisors, so it's a prime number. Furthermore, 17 can be written as 2 plus 3 plus 5 plus 7. Now, what's so special about that? Well, apparently, if you know that 2, 3, 5, 7s are also prime, like they've got only two positive divisors, 1 and the number themselves. So, moreover, these are the first four prime numbers in our list, and their sum turns out to be another prime, which is quite astonishing. Here's a fun fact which is pretty funny. Did you know few people are scared of the number 17? Such people are said to have heptodecaphobia. Then, furthermore, one of the reasons why people are scared of this number is the fact that if you write 17 in the Roman system, it turns out to be XVII, which is just an anagram of VIXI, which in Italian means I'm dead. Okay, not a really good thing to talk about. So yeah, it's scary for the people in Italy. They probably don't like this number much. Further, did you know Apollo 17 was the final mission of NASA's Apollo mission? Well, it's pretty funny and coincident. Also, have you heard about the famous number puzzle, so-called Sudoku? It's basically a number puzzle in which you have to fill in the whole table, and it has actually you get some clues of that game, and you just need to fill up the table. So it's mathematically proven that you need at least 17 clues to complete the whole puzzle. Otherwise, it won't have any unique solution. So 17 is pretty it's interesting number. Also, if you know that according to MIT, in the interval 1 to 20, the most random number you can ever find is 17. So in the same time, it's a very random number. In the same time, it has got really great properties. So a matter of fun. Now, in this talk, I'll be talking about prime numbers because 17 is a prime number, and I'll be stating a really good journey how the prime numbers developed, what were the topics discussed in the history, and how the current research is going on in this field. So, as I already told, a prime number is a number that has exactly two positive divisors. Say, for example, 7. 7 is a prime number. The only positive divisors you can find are 7 and 1. So here are a few infinite. Here's the infinite sequence of prime numbers that starts with 2, 3, 5, 7, 11, and so on and so forth. Apparently, I should refrain myself from saying infinite sequence because that's the first thing that comes in your mind. How many prime numbers are there? Are there infinitely many primes or a few of them? Before we jump to that question, I would first like to ask you a question. Why do we even care about prime numbers? What has it got to do with math? So if you look precisely, then prime numbers are uh, basically the building blocks of all the numbers in the number system. So for more precisely, we have the fundamental theorem of arithmetic, which you might have studied in your high school. It states that any positive number, integer greater than 1, can be expressed in a unique fashion of product of primes. Say for example 6, 6 2 times 3, 36 can be written as 2 times 2 times 3 times 3, and so on. So basically any number can be written as product of primes. So all the set of primes generate all the natural numbers in our number system. So they are kind of a building blocks, and we do care about them because studying them basically reveals mostly about all the numbers we have. So now we come to back to the question, how many prime numbers are there? So before going to that, we first note how to uh, find all the prime numbers given in a certain bound. So we have got the sieve of Eratosthenes. It's basically an algorithm to find all numbers up to any given limit. Here's this picture. So basically what does the algorithm do is it just starts with writing out all the numbers you have up to the given bound. Then you start with the first number, that is 2. Then you just cross out all the multiples of 2 from that list, like this. You start with 2, cross all the multiples of 2. Then you go to the next uncrossed block, and then you count that in the list and then cancel out all the other numbers in that list that are multiples of 3. And similarly, you do with the next number and so on and so forth. So in this fashion, what you are doing is you are just finding out those numbers which cannot be written as a product of previous any number. So of course, they'll have just two positive divisors, that's 1 and the number themselves. And so you get the primes of all these numbers. So the point is this method actually just tells us that in a given bound, you can actually find all the primes. But it doesn't tell us anything much about how the primes are distributed or how many primes are there or any bound about that or how does the number of primes up to a given bound behave. So it's just an algorithm to see how primes are like arranged. So later on, Euclid came into the picture and he first stated that there are infinitely many primes. The proof is pretty interesting and elementary, and I hope many of you have seen this before. This is not my writing, I just found it somewhere on the internet. So basically, what the proof states is it starts with the assumption that suppose there are finitely many primes, and if we just get a contradiction, that would mean that there are infinitely many prime numbers. So the proof basically starts with assuming that there are finitely many prime numbers, and you just suppose if they are finitely, you can just list them off by p1, p2, dot, 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 pn. So now we just construct a new number given by p equals to the product of all these primes plus 1. What does this plus 1 do is it kind of violates the our fundamental theorem of arithmetic. Like what the fundamental theorem of arithmetic says is any number p can be written as product of primes. Now clearly our p cannot be a prime because we assume that all p1, p2, pn are the only primes we have. So P must be a multiple of at least one of them, like at least one of the PIs. However, if you just divide this number P by any of P1, P2, dot, 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 you always get a remainder of 1, which clearly means it's not divisible because if it would have been divisible, then it would have been a remainder 0. So this statement is kind of absurd and contradicts the fundamental theorem of arithmetic. So we get a contradiction. That is, there are infinitely many prime numbers in the number system. This was a great result, but again, this really doesn't tell us anything much about prime numbers. It's just a way to show that there are infinitely many prime numbers. We still don't know how they are distributed, at least how the prime behavior exists, and so on. So, a really interesting proof of Euler showed that the number of prime numbers up to n is at least logarithm of n minus 1, natural logarithm of n minus 1. So it kind of shows how the bound behaves. The proof is pretty interesting exercise to try. I'll just state the proof over here. It starts with the fact that any ith prime is at least I plus 1. Say, for example, our p1 is the first prime, that's just 2. That's greater than equals to 1 plus 1. Our second prime is 3, and that's greater than equals to 2 plus 1, and so on. So our all ith primes are at least I plus 1. It's pretty easy to prove, like just by induction. So what Euler's proof was, it's basically on the motivation of the sum of infinite GP you must have heard about, that this sum to infinity equals to 1 over 1 minus a whenever moduli of a is less than 1. So basically, this equation is really interesting because if you see one part is interesting for us, and the other part is something we can calculate. So what we do is, from your normal calculus class, you must have noticed that about the Riemann sum, in which you can bound this harmonic sum of 1 over 1 plus 1 over 2 dot 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 1 over n using the Riemann sum integral. Like, you can just take the area under this curve. So this thing actually turns out to be less than equals to integral of 1 over x dx from 1 to n. That's just the area under this curve. So, and that's just natural logarithm of n. So we get this inequality right over here. Now, suppose that there are k primes till n, that's just k equals to pi of n. So we can obviously say that this sum is a part of this sum, that is sum of all those reciprocal of those numbers which are only divisible by all these p1, p2, dot, 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 pk. So obviously this sum contains this value, so this will be at least this. Now, this can be further written as a product of, using your combinatorics, that this can be written as a product of all those primes I equals to 1 to k of 1 plus 1 over p 1 pi plus 1 over pi squared plus dot 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 infinity. Because here n2, for example, can range any value from 0 to infinity. And similarly, so in this case, we are ranging the power of pi from 0 to any infinity value. So when you just multiply, you just get this whole combination. So this is in fact equals to this thing. Now here we use our sum of infinite GP formula to just get this result, because the summation is nothing but 1 over 1 minus a, and in our case a is 1 over pi. So we get this thing. And now, using our inequality that pi is at least I plus 1, we can just replace pi by I plus 1 over here to get that this thing is greater than equals to this thing. And this is actually a telescopic product. Like, if you just expand it out, it becomes 2 times 1 times 3 by 2 times 4 by 3 and so on up till k plus 1 by k. So these things eventually cancel out, resulting in k plus 1, and our k was just pi. So we showed that pi of n plus 1 is at least n plus ln of n. So here we get this result. What's special about this result is it shows us that the pi function grows at least as fast as the natural log of n. So it's a pretty cool statement. Later on, Gauss, he's a really cool guy. In his teenager time, he made this conjecture that the value of pi of n is asymptotic to n over ln of n, which is further asymptotic of li of n, which is nothing but integral from 2 to n of 1 over log x dx. Now, what does this tilde sign mean is, if you just take this whole thing under this fraction and increase the value of n, as n increases, this ratio tends towards 1. That is, the value of pi of n behaves roughly like n over log n. So he just formulated this data in his teenage time. You can see, like, till 1 to 100, there are 25 prime numbers, and the value of ln of n, x over ln of x, is 22. And as you increase the value of x, these results are approximately the same. So he conjectured that pi of n is asymptotic to n over log n. Now, you must have heard about the famous Riemann's hypothesis. Riemann was actually interested in the Gauss problem, Gauss conjecture. He actually tried to prove it. He submitted a 8-page journal, an 8-page research paper in a journal, in which he proposed a possibility of how we can prove Gauss conjecture. He actually figured out the value of pi function in terms of the lie of x, that's just the integral of 1 over log x, and the non-trivial zeros of the zeta function. Ooh, what's the zeta function? Zeta function of s is defined as this infinite sum. So now, of course, this is only true when real part of s is more than 0, because if you just take s to be negative, then this will become reciprocal and the sum will diverge. So yeah, he stated that if we can prove that all non-trivial zeros of zeta of s have real part half, then Gauss conjecture is true. But however, he was not able to prove the statement, so he just made a hypothesis that this might be true, and he stated that it would be really desirable to see a proof of it. Riemann hypothesis still seems to be an open problem for everyone, and in fact, it's one of the 5 million problems offered by the Clay Mathematical Society. So if you prove it, you are getting $1 million. Yeah. So the Riemann hypothesis has got really great stories. You might be knowing about G.H. Hardy. He actually was on a voyage in a ship and he wrote a letter to his friend in a postcard saying that I have a proof of Riemann hypothesis, but the margin is too small to contain it. So it kind of resembles with the story of Fermat's last theorem. Fermat was another mathematician, and he stated a theorem uh, at the end of his life, which was the equation a to the n plus b to the n equals c to the n has no solution in integers if n is greater than equals to 3. He just stated that he has a really remarkable proof of this statement, but the margin is too small to contain it, and then he died, sadly. So this remained to be an open problem for a while until Andrea Wiles proved it recently. So Hardy thought that his relationships with the god is not so great. So saying this postcard will prevent the boat from sinking. So let's analyze zeta function a bit more. We just saw that this definition works when real part of s is positive. Actually, if real part of s is negative, this function can be further be written like by using analytic continuation, which is a part of the complex analysis. What you basically do is you just plot the graph of zeta of s, and then you try to find a similar behaving graph in the like the left side of the complex plane. So it can be easily found that if real power of s is negative, then the analytic continuating function for zeta of s is given by this. This is when real part of s is negative. Why I'm stating this? It's because you might have heard about these two famous results by Euler and Ramanujan. That zeta of 2, that's 1 over 1 squared plus 1 over 2 squared, dot, 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 so on till infinity, is pi over 6. It's actually pretty famous. And one of the crazy lines by Ramanujan was 1 plus 2 plus 3 till infinity is negative 1 over 12. And if you just plug in negative 1 over here, even though it diverges, you get this sum. So basically, he claimed that zeta of negative 1 is minus 1 over 12. Again, makes no sense because this sum is clearly divergent. However, for G.H. Hardy, this was a really deep point because if you just plug in negative 1 over here, you get this whole quantity is equals to this. Gamma of 2 is nothing but just 1 factorial, so it's just 1. And if you do the math by plugging in zeta of 2 by pi by 6, canceling out things, you eventually get that this thing is equals to negative 1 over 12. Surprising, yeah. So basically, it had a really deep connection with the Riemann hypothesis and the zeta function. Okay, so this is how things work in mathematics. You think over a problem, work over it, try to analyze it in a better sense, make conjectures. Other people try it, create more conjectures, and the process continues to work on. Riemann hypothesis is still an open problem, and you can try it if you want. Okay. Finally, the prime number theorem was proved, that is the Gauss conjecture, by Hadmard in 1896. He in fact proved the Gauss conjecture that pi of x is kind of similar behaving to x over ln x. He used the analytic number theory. And so, yeah, so basically, now the point is the Riemann hypothesis proved the prime number theorem. So if prime number theorem is already proved, why do we care about Riemann hypotheses? Well, apparently there are many mathematical results that have been found assuming Riemann hypothesis to be true. So if one can prove this, a lot of comments can be made about prime distribution in the number system. So it's really a very important result for us, and if proved, it will be a groundbreaking achievement. So again, prime number theorem does not necessarily imply prime number Riemann hypothesis. For example, suppose in your basic algebra class, you are said to be proved that sine squared x plus cos squared x is 1. One way to do is just multiply 0 by both sides, and you get 0 equals to 0. Yay, proved. Well, no. What you did was you said that this statement P implies truth. However, when you are said to prove this thing, it's actually the other way, that truth implies this statement true or not. Well, if can you start from zero equal to zero and prove this back? Well, depends if you know the proof. So in a similar way, Riemann hypothesis implied prime number theorem, but if prime number theorem is proved, it's not implying that Riemann hypothesis is true. So works are going on in this field, and let's see what happens. A few more interesting problems to work on are Goldbach conjecture. I'm kind of deeply connected with this problem because, like, when I was in grade seven, my maths teacher gave me this problem, and he didn't tell this is an open problem, and he just said me to work over it. So I kind of worked over it for a week or two and then showed him my result. However, my final conclusion was again an open problem and nothing really happened. But like it was pretty inspiring for me, and I started enjoying mathematics from that day. I started writing my own theorems, submitting it to various PhD professors. In fact, I got an invitation for 2 months research work at Eastern Research Institute because of my theorem on generalized factorial function. And then there I worked with various PhD students and professors and finally got 2 papers published in a peer-reviewed journal. But anyways, get to the point. So Goldbach conjecture states that every prime number greater than 4 can be written as sum of 2 primes. So say for example, any prime number. Say for example, we take 12. This can be written as say for example 5 plus 7, prime plus prime. If you take say for example 10, 10 can be written as 7 plus 3, again prime plus prime. So it's basically saying that any prime number can be any even number greater than 4 can be expressed as sum of 2 primes. It's still an open problem in the additive number theory and pretty interesting to work on. There was a weaker version of the Goldbach conjecture which stated that every odd number greater than 5 can be expressed as sum of 3 prime numbers. So, say for example, if you take 7, then 7 can be written as 2 plus 2 plus 3. That's a prime plus prime plus prime. This weaker version was recently proved, and it uses the method of the circle method found by G.H. Hardy, Ramanujan, and related work. So, what the circle method is, it's basically a technique to deal with additive number theory problems. Additive number theory problems are basically finding solutions for equations like this, where x and y belongs to some sets. Say for example, that's fine. So what you basically do is you try to find the number of solutions to this equation related to an integral and try to bound that integral on the unit circle in the complex plane. But anyways, another problem from additive number theory you can work on is the Sophie-Germain conjecture. It's not my writing. I found it somewhere on the internet. So Sophie-Germain prime is a prime P such that P and 2P plus 1 both are prime numbers. So say for example, 5 is a prime Sophie-Germain prime because 5 is prime and 2 times 5 plus 1, that's 11. That's again another prime number. So the Sophie-Germain conjecture states that there are infinitely many Sophie-Germain primes. Now, why do we categorize this problem as an additive number theory problem? Well, if you just solve the equation x plus y equals to 1, where x belongs to the set of prime numbers and y belongs to the set of negative twice of prime numbers, that is numbers like minus 4, minus 6, minus 10, and so on, then any solution to this equation will correspond to a Sophie-Germain prime. Okay, because you see 1 plus twice of p is a prime number again, so y will be a Sophie-Germain prime. So this is again a part of additive number theory and can be kind of handled using the circle method, but it's still an open problem because that bounding part is pretty hard. So yeah, that's it. Thank you everyone, hope you enjoyed the talk.
Thank you so much, Anand. You really well explained everything very well, and thank you so much for sharing the information and knowledge. Before we move towards the conclusion, I would really like to ask you one question. What is your daily routine since you have achieved so much? So, what all things you do on a daily basis? I think we all would really like to know that.
Okay, so basically, I wake up in the morning, and then it's not like you just have to study all day. It's basically you just need to find a subject that you find interesting, and if you find that interesting, you can just study it anytime, anywhere. Like even if you make anyone interested in some subject as at say for example 3 a.m. in the morning, he will be willing to do that. So it's not really about the routine, it's about the interest. So if you are just interested into that, you can just spend a lot of time over that, and the more you spend, the more you gain. That's the simple philosophy.
Very well said, Anand. It's all about the interest which is generated in your heart and mind and which keeps you do the things. So, who is your inspiration? Who was actually the person or anyone who ignited the spark in you about maths?
Okay, so I will give all the credit to my father. Like when I was in seventh, I started writing theorems, but like few people used to say, "What are you doing? You just need to do the schoolwork. It really doesn't help you in your current studies." But my father thought that I had something really interesting in myself, so he started looking for a platform for me, and then he always said me like if you have passion for something and you are completely determined into that, nothing can stop you from being happy, and that's the goal of the life. You need to be happy. So he really supported me all the time, no matter what other people said, and I think whatever I am right now is because of him.
That's great. So you actually proved your father correct and right at every step of your life, right? So, do you have any suggestion, any advice for the children of your own age? And we have many children here also. So, anything you want to tell them?
Okay, sure. Just follow whatever you like. If playing is your passion, go into that and get great achievements in that. You just choose a particular field in which you want to excel and then just show your 100% no matter what others say.
That's very well said. Very, very well said, Anand. So, thank you so much, Anand. You are really doing great and remarkable in the field of mathematics. And we wish you best of luck for your future endeavors. We would be great and we would be honored for your new achievements. And I also would like to extend my vote of thanks to everyone present here for taking out your precious time and listening to us. So, thank you, everyone. Thank you so much.